one language Calabi-Yau Compactification. Thank you. So I believe I have 45 minutes. Thank you. So it's a great pleasure to be here and talk to the mixed audience of physicists and mathematicians who are interested in talking related to each other. And I hope to give something for each. And so this is actually work that I've been doing with Christopher Keller, and we hope to write it up very soon. And there are two motivations of this work. One is that to note that there is a life beyond the BPS sector. So there have been lots of very interesting talks already given and will be given about the BPS states and their properties in supersymmetric quantum field theory and related string theory, and very much is known. But especially to mathematician, I'd like to first point out that that's not all there is about quantum field theory and string theory. That there are lots of interesting things happening in sectors that are not BPS. Here I'm using the word hybrid, but for this talk it essentially means BPS. So there are things we can say. First of all, those people, those non-BPS states are there, and it's interesting to understand them. And then, so today I would like to report on some modest progress in exploring this territory which is not very charted. And especially in the case of N=2 supersymmetric sigma model in 2 dimensions, whose target space is Calabi-Yau manifold. So that's one motivation. And second motivation is that there is this conjecture, and I had a very interesting conversation with Professor Yao yesterday, that there is some kind of belief that there is only finite number of topological types of Calabi-Yau manifolds. And there are some good, these are very well motivated conjecture. And if so, then in particular it would mean that there must be a bound, global bound on the total number of Hodge numbers. So I was curious to find out if you force to consider some Calabi-Yau manifold whose Hodge number is extremely large, then there might be something interesting happening. If we understand what that is, then we might be able to get some insight into this very important question, interesting question in mathematics, but it's also very important in physics, for example, in the context of landscape of string vacuum, etc. So I'd like to say something about that. So in case you got totally lost during my talk or lose interest or you have to go somewhere else, I'd like to just tell you the punchline of my talk so you can just go to sleep afterwards. And so this is one of the results. This is not the only result, but this is a typical kind of result. So suppose you consider Calabi-Yau manifold with sufficiently large Hodge number, I'll quantify it later. Then I can prove that there are non-chiral, namely non-BPS highest weight state in the Hilbert space of this conformal field theory, whose left-moving conformal weight and right-moving conformal weight, these are these are eigenvalue of L0 operator for the Virasoro generator, so namely the conformal dimension for left-moving Virasoro and right-moving Virasoro is less than 2/3. For your reference, in this kind of sigma model, there are primary field, primary state. There is a ground state, which is clearly primary, and the first non-trivial primary state has this number equal to 1. So this is actually lower than the first non-trivial BPS state of the cell. So there is, first statement is that there are non-BPS states whose dimension is lower than the first non-trivial BPS states. And moreover, the number of such states grows linearly as you increase the Hodge number. So that means that you have a very narrow band between the ground state and the first excited state, and the excited state where you have this non-BPS state. And the number of states in this domain grows exponentially. So that means that the state in that area becomes denser and denser as you increase the first state. Sorry?
You wrote linearly, you said exponentially.
So what I meant is that number of such primary states in this domain dimension grows linearly in Hodge number. I will please tell you precisely. So that's the result. If you are interested in that, please stay after. Otherwise, we can give and I will not be open. This is the derivation of this is extremely elementary. And but however, unfortunately, I'm going to use physicist notation and the physicist language, so it might not be clear. But since the method is extremely elementary, if you have questions, please do ask. So first of all, I'd like to summarize what's known about the BPS sector of the cell. So this is actually fit very nicely with Don's ideas talk that we just heard. We had a very much pleasure of listening to his presentation. And so I'd like to make use of some of the terms he introduced. So I'd like to consider N=2 supersymmetric sigma model whose target space is Calabi-Yau D complex dimension. All these theories, two-dimensional conformality theory, has symmetry, very large symmetry of N=2 super-conformal algebra, super-Virasoro algebra. We have Virasoro generator, which is with additional supercharges and U1 charge. And on the top of that, this Calabi-Yau manifold has unique holomorphic B forms, which implies that there is a symmetry in the Hilbert space called spectral flow, which is very important for the space-time supersymmetry, for example. If you use this theory to construct a string theory model, then this is closely tied to supersymmetry in the target. This enhances this worship symmetry. So for example, if you consider Calabi-Yau twofold, which is K3, then this N=2 super-Virasoro symmetry is enhanced to N=4 super-Virasoro symmetry. So you have Virasoro generator, instead of one set of supercharges, you have two sets. And then instead of just one current, you have SU2, affine Katsumudi algebra. So you have an enhanced symmetry. And then there are similar stories for other dimensions too. So this is going to be enhanced. And I would also like to point out that this is the symmetry of the theory, so that in the Hilbert space can be decomposed into some of the irreducible representations of this algebra. But on the top of that, for physical conformality theory, there is a left moving sector and right moving sector, namely holomorphic sector and anti-holomorphic sector. So that means that you actually have two copies of these generators. So that means that represent a Hilbert space of this conformality theory can be decomposed into sum of products of representation of these. Product, I mean one for left mover and one for the right mover. So this is a very important point that I will exploit for the rest of my talk. I'd like to briefly tell you what kind of representation we have in mind. So basically highest weight representation, that we are interested in highest weight state, which are narrated by this positive frequency mode of the super-Virasoro algebra. I'm using N=2 notation. Highest weight state is an eigenstate of L0, which is delta. This is a delta that came out in this summary here. So this is a left moving part of delta. And then there is another copy here for the right mover. And it's also eigenstate of J0. So delta and Q meet. Unitarity of the representation, namely that the representation having positive definite inner product requires the delta being greater than half times absolute value of Q. When delta hits half of Q, you have a possibility of having chiral representation or BPS representation in the terminology that has been used in this conference. So those have additional features that they are narrated either by this one or this one. Sometimes one of them is called BPS and the other is called anti-BPS, but I'm just going to call them BPS. And their delta, the eigenvalue of L0, is related to exactly equal to half of Q. And so that means that if you have generic representation where delta is greater than half of Q, and if you lower the delta to this band, typically irreducible representation of this type becomes reducible and becomes some of these chiral representations that I will show you in the next couple of transcripts. So these are kind of, so today I asked other Virasoro generators to grow the entire representation. So as I said, this is a symmetry of the theory, so that means that Hilbert space can be decomposed into product of representations of this type. Explicitly, we're going to use two types of representation corresponding characters. And so this is for N=2 algebra, but it's going to be extended by spectral flow. And this was studied by Odake in 1990. This I think was his PhD thesis. And so for chiral representations, there are actually for d-dimensional Calabi-Yau, there are d inequivalent BPS representations, all of which is delta equal half of Q, and Q have d choices here. And non-BPS one, there are d minus 1 irreducible, inequivalent representation. And again, delta is greater than half of Q, etc. I'm going to denote the character of this by chi, just because this is chiral, so I call that as chi, just to remind myself. And then non-chiral ones, characters are denoted by CH. As I said, there's a relation between chiral representation and non-chiral representation. If you start with non-chiral representation where delta is greater than half of Q, reduce delta so that it hits this bound, then it can be decomposed into some of chiral representation like that. And this combination is dictated by the fact that it is exactly this combination in which Witte index vanishes. For chiral representation or BPS representation, Witte index is non-zero. And these are the formula for the Witte index for chiral representation or BPS representation. And if you take this combination, they cancel out. As they should be, because massive or non-chiral representation has no Witte index. Is this notation, are these notations clear so far? Because I'm going to use this for the rest of my talk. Sorry? D is a dimension, complex dimension of Calabi-Yau manifold. So it's proportional to the central charge of the Dirac value. Now the partition function of the Hilbert space is, as I said, the Hilbert space is decomposed into sum of product of representations, n equal 2 on the left and n equal 2 on the right. So we can expand the total partition function of the theory by sum over these kind of things, where you can have a sector where both left and right moving sectors are BPS, called half BPS. Or you can have a situation where the right mover is BPS, but left mover is not. Or the other way around. Or you have a situation where both left mover and right mover are non-BPS. So there are 4 sectors like that, and I would like to go through each one of these sectors. First of all, this half BPS sector. Half BPS sector is completely controlled by classical topological structure, the Hodge number or Betti number of the Calabi-Yau manifold. So you can so first of all, there's a unique ground state. Q naught, chi naught is a character of the ground state. So this multiplicity is known to be 1. And then you have this kind of summation where these are related to the Hodge number. Just as an example, if you choose Calabi-Yau 3-4, this sector partition function can be expanded in this way where this is the ground state, there's a unique ground state. And then the proportionality constant multiplicity of this is related to H11. Multiplicity of this is related to H21. There is no cross term like that for compact Calabi-Yau manifold. Otherwise, well, actually you can prove that there is no such cross term. So that's this sector. This is the simplest. Now let me move on to the next sector. This crossing term, this is essentially the complex conjugate of this. So they have the same structure. So this has a structure that we have a mixing of chiral or BPS representation and non-BPS representation. And it turns out that this coefficient here is essentially determined by the elliptic genus of the Calabi-Yau manifold. Elliptic genus is defined in such a way that you choose this sector, you replace this by Witte index and compute the same thing. You can do that by noting that if you these term theta are the same term theta that appeared in Gonzaguier. So where e to the 2 pi I tau, which is q, measures the number that measures the eigenvalue of L naught, and theta measures the eigenvalue of J naught. And since you have left mover and right mover that are both horomorphic and non-horomorphic components, you choose theta bar in this value, and what it does is effectively turn this character, BPS character, into Witte index. So if you do that, this becomes of this form. This looks a little bit messy, but what it is that it's a horomorphic function of tau and theta, and it knows about this kind of multiplicity functions. And by the modular invariance of the partition function, which is required by consistency of the conformality theory on 2-dimensional force, you can show that J is a Euclidean atomic form of weight 0 and index d over 2, where d is a complex dimension of the Calabi-Yau manifold. Great thing is that space of such Euclidean atomic form is unique. So that means that if you know first Q expansion coefficient of J, it's uniquely determined. And therefore all these coefficients are essentially determined. And this is very useful. So let me give you a couple of examples. So first example is a case of Calabi-Yau twofold or case 3. And in that case, in fact, it is totally determined solely by the fact that there is a unique vacuum in the system. So that fixes this to be 2. And then the rest is uniquely determined. For example, this 20 is totally determined, and 20 is related to the H11 of case 3. And all these are related to some higher homology. So it was actually my PhD thesis, which those are here historically is talk about representation of character of n equals 4 representation. Interesting thing is that, for example, this Kainok and Taiwan are related, expressed in terms of appel-Lerche sum. And I think that was the first instance where appel-Lerche sum and modular forms appeared in physics literature as far as I know. And I was curious to know that this property of this number, which is what I did in my PhD thesis. And to my surprise, all these came out positive integer. In principle, since it's related with index, it could have been negative. But one can deduce that if there were a negative number, then symmetry of case 3 sigma model is generically greater than n equals 4. And the fact that all these are positive integer means that there is no generic symmetry enhancement. So the positivity of this integer has a very interesting property. So I was actually fascinated by this number for many years. And just a couple of years ago, I was meeting with Toru Eguchi and Yuki Tashikawa. And Eguchi had this obsession about M24 symmetry of case 3. So we talked about it, and we thought maybe these numbers have something to do with that. And fortunately, on my laptop computer, I have the Japanese Mathematical Society edited encyclopedia of mathematics. So we looked it up, and then I noticed that all these numbers are actually dimensions of the irreducible representation of M24. And so I just leave it like that because there probably will be some talk about it later today. But I think this is very curious fact that should be telling us something interesting about case 3. But I move on to the case of Calabi-Yau threefold. So Calabi-Yau threefold, it's a special feature of Calabi-Yau threefold for any odd dimensional Calabi-Yau manifold is that index of the vacuum representation is 0. So it actually starts with a non-trivial chiral primary state, and then also sum over non-chiral state, non-BPS state. And since the dimension of the corresponding relevant Jacobi form is still one-dimensional, so that means that this Euler characteristic of Calabi-Yau threefold totally determine the normalization of the Jacobi form. So therefore, the elliptic genus has to be proportional to chi, the Euler character, and times the basis. Okay, so for a long time I thought that therefore, in this case, elliptic genus is not that interesting because it doesn't contain as much information as case 3 case, but I was wrong because it does tell us something interesting, which I will explain, which is the following. That so this is, it turns out that this first term here is actually by itself the Jacobi form, which I do not know for a long time. And so what it means is that all these terms should not be there. So namely that this should be 0, this should be 0. So that means that these are 0. These are equal to each other. So that means that in fact, even though I said that we are talking about the mixing term of non-BPS and BPS state, but if you have this property, what happens is that BPS state combine into non-BPS state altogether. So essentially we can say cross term is equal to 0 in this case. So that's a very non-trivial thing that comes out from this kind of property. But I said generically because the reason is that we cannot exclude the possibility that we have this kind of cross term, where cross term with a vacuum representation, because the index of the vacuum representation is 0. So even if there were such term, cross term, it would not have shown up in the elliptic genus. But if you have such terms, that means that you have an enhancement of symmetry on the worldsheet itself, which would not happen generically for Calabi-Yau sigma. So for the rest of the talk, I will consider a generic case where there is no such mixing term. But in fact, it's not so difficult to generalize or extend our result in the case where this is not equal to 0. But in the interest of time, I'm not going to discuss it. But this can be done.
But that doesn't change the balance?
Not very much. So in case you got lost during all this discussion of the elliptic genus and the Lerche sum, etc., so I'd like to summarize what we have seen so far. So essentially, for Calabi-Yau 3 form, that can be stated in the following way. So this is basically telling you about the structure of the Hilbert space of the conformal field theory. If you look at the partial function, which you can evaluate using trace of the Hilbert space, you see that there are BPS states, these are hard BPS states, controlled by the fact that there is a unique vacuum here, H11 and H212 in the case of Calabi-Yau, and then there is no generic mixing term. And then there is an entirely, what you are left with is an entirely non-BPS state. So this has been the state of knowledge about this conformal field theory until this year. And what I would like to report today is the structure of this non-BPS sector. Any questions so far? Okay, so then I would like to move on to tell you our work. So I would like to tell you some new results about the non-BPS section of this field. So basic idea is very simple. So we want to exploit the modular invariance, and I will restrict myself to the case where tau, the modular tau that appears in those case also, to be pure imaginary. For simplicity, we can generalize this, but I assume that the pure imaginary is positive imaginary part. I set theta equals 0. In that case, the modular invariance would imply this kind of equation, where partial function can be expressed into some of these exponential like that. So you have a primary state and then you have descendant. So but then what you notice is that suppose x is greater than 1, then if you look at each term here, this kind of term which appears here is smaller than this kind of term which would appear here if delta plus delta bar is greater than c over 12, where c is a central charge of the Grassel line. Because this is true, this is greater than 1, so then if x is greater than 1, x is greater than 1 over x, so evidently this is smaller than this one. So that is this kind of very simple equation. This is all I'm going to use today, essentially. So this is a very simple fact that the junior high school student understand. And then, so that means that something interesting. Suppose you take a difference between this and this, and that should be equal to 0. Something being equal to 0 means that it has to have both positive part and negative part, and they should cancel with each other. But this means that most of these are positive, because there are infinitely many representations with large delta. But there are only finite number of states with delta plus delta bar less than c over 12. And they are the only ones which contribute positively to this one. So by knowing something about the property of state with delta large, you can deduce something about the number of states for low conformal rate. So that's the only idea I'm going to use for the rest of my talk. So this already shows that existence of state of small conformal rate, because if there are no such state, then everything that contributes to this summation could be negative, and there is no way that sum of negative number becomes 0. So that's sort of the first step in showing the existence of a state of this type. What I'm going to do the rest of my talk is basically strengthen this kind of statement by taking advantage of our knowledge of Hodge number and derivative genus. For specific, this is true for any conformal field. And then what I'm going to do is to apply the same idea in the specific case of n equal to sigma model with Calabi-Yau target space by taking advantage of the additional knowledge on Hodge number and derivative genus. That's true. So that's why, because then we can separate these cases. So I would like to define the following kind of thing. So let me go back. So partial function has these forms of chi is BPS characters and CH are non-BPS characters. By combining this, I'm going to define these two kinds of functions. And the reason I consider this kind of function is basically because I'm taking the difference of this kind. I'm interested in evaluating partial function at x and partial function at 1 over x and takes a difference. So I'm doing that at the level of each character. So then we can show that this equality that z at x and z at 1 over x equals 0 can be expressed as this kind of summation. I'm just rewriting this equality in terms of each character, and it can be expressed in this way.
Sorry, this is for
Calabi-Yau threshold. And we can show that G naught, so every function is known, although it's expressed in a rather ordered way in terms of Appel-Lepche sum. But you can show that G naught is a positive function for all positive x greater than 1. G11 is negative, so we know that this contributes positively, this contributes negatively, and this essentially follows from the observation Greg just mentioned. For this summation, Barton representation contributes positively, and this contributes negatively. How about this gamma thing? Well, gamma depends on actually highest way of the non-BPS representation. So I want to define, so basically what happens is that when delta is small, this is positive, but when delta gets large, it becomes negative. So I'm going to define some function which distinguishes the value of delta, which gives you some kind of boundary value of delta, which distinguishes positive gamma and negative gamma. So I'm going to define s of x as a function of x as supremum of delta plus delta bar, for which this is positive for any q and q bar. So that's the definition of s of x. So then you can show that this equality can be turned into this inequality, because if you restrict, so this is sum over all non-BPS representations, but if you restrict your summation to be s of x, delta less than s of x, then all these contribute positively, and what you are neglecting are negative contribution. So if you ignore that, you can get an equality like that. Where this is positive, this is negative, so I put absolute value to distinguish this part. And the next step is now to estimate this function. And we can expand it in the first few terms and easily come up with an estimate that this is always bounded by this kind of exponential function. We can improve this further by going to higher expansion, but for the purpose of simplicity, let's stop here. Then you can prove that this equality, which turned into this inequality, can be further simplified as this kind of inequality. Because now you are replacing this by the same function. So essentially the left-hand side is not just counting the number of possible representation which is bounded by s of x. So now we can give a lower bound for a number of non-BPS primary states with low dimensions, expressed in this way. And so here essentially is an explanation of our result, because if you look at the right-hand side, you have something which is proportional to the sum of total Hodge number. So you see that the number of states like that grows linearly in Hodge number. So this is already showing that where we are heading. So now this inequality is true for any x. So that means that for each x greater than 1, you get some bound of the number of representations. So we can try to evaluate it at your convenient places. And so we try that at 2 convenient places. That does not mean that we have gotten the best bound, but we did get some bound. And so let me show you what that is. So this is an inequality. So remind you that s of x is defined to be supremum of delta plus delta bar, where gamma is positive. And so this is actually something that you can evaluate very explicitly by using the representation of n equal to characters, n equal to algebra. So this is very well-defined set of well-defined number, and it's bounded by that. So that means that so this is already, I already said, but for large h11 plus h12, this gives non-trivial constraint. So let us study its consequence. We can do that for any x, but let's check it at these two limits. First, x goes to 1. As x2 goes 1, in fact, s of x goes to 0.6555. That's roughly two-thirds. And so there we find that the non-chiral primary with delta plus delta bar less than 0.655, etc., is greater than numerical number times the total Hodge number minus 492.6 ... So this inequality is meaningful for large Hodge number Calabi-Yau whose size is greater than 493, and this as h is greater than that, as Hodge number is greater than that, number of non-chiral primary with this kind of very small conformal way grows linearly as a function of the Hodge number. Now, I believe, I don't know exactly who are the co-authors, have some interesting results about the global bound on the total Hodge number of elliptically fibered Calabi-Yau manifolds. And if what is here, he can shout out what was that number.
Yes, I think it's 494.
494. That indicates that there is at least one example.
So that's a bound on H21.
Yeah, so that means that H21 plus H11 is, I think in your case that H11 is like 11 or something.
Yes,
Anyway.
yeah, so I don't know how to prove a bound on H11 plus H21, but for elliptically fibered, there's an upper bound on H21.
Right. So there are examples like that, but in fact, the interesting thing is that at least for elliptically fibered Calabi-Yau manifold, this is on the cusp of getting to the maximum bound. I don't know, of course, I mean, there are many Calabi-Yau which are not elliptically fibered, so if there is a bound that maybe that can be larger than that. But interesting that the Hodge number where this kind of inequality starts kicking in is close to the maximum amount of Hodge numbers that you can possibly have for this type of the elliptically fibered. And since they are on, the number of such low lines stays low linear. Okay, so we can also look at the other limit, and the other limit, the bound is actually a bit much better, because S infinity is now quarter rather than 2/3. So you can show that asymptotically that you're going to have lots of states whose conformal weight is now bounded by quarter. But in order to achieve that, you have to have a very exponentially large Hodge number. You have to consider exponentially large Hodge number. So that's another result. Okay. And you can of course scan the intermediate region and see what kind of the best bound you can possibly get, which we have not done. There are alternative approach to this kind of program, which was actually pioneered by Shimeon Tellerman. And there he actually noticed that if you parameterize the torus modulus tau, then if you express it in terms of S, then the modular invariance can be expressed as a reflection of S. So that means that if you take one derivative of Z and evaluate it at S equals 0, namely tau equals I, or three derivatives, they should all give you 0. And that can also be thought of as a consequence of the modular invariance. So we can try similar thing in our case. So but here we can exploit the theta dependence. So we parameterize tau theta in this way and looked at a similar kind of derivative operator which should vanish by the modular invariance and looked at its consequence. In the interest of time, I would like to skip the detail. I do not go into too much detail, but the idea here is that, again, we would like to put bound on this non-BPS sector. This is the half BPS sector, the quarter BPS sector. These are completely fixed by Hodge number, and they're essentially fixed by the elliptic genus, modulo non-generic situation. So then, we know that this derivative operator acting on the total thing should be 0, this acting on the total thing should be 0 when evaluated at this number. But we can take some particular linear combination so that this subsector can also be annihilated by differential operators. And if you do that, then the remaining part should also satisfy this kind of equation. And interesting thing is that this coefficient can depend on the Hodge number because its age is determined by this equation. And for each representation, you can have this kind of property. So we can exploit this property. So without going into detail, what we find is that so this is a horizontal. This horizontal axis is a total Hodge number, and the vertical axis is denoted by this notation. But what it means is that the conformal dimension delta plus delta bar, which is sort of upper bound, and you have to have operator below this bound. So this kind of bound can be expressed in terms of derived in terms of this from this kind of analysis. I can explain in detail what we are doing, but probably it's not very illuminating to most of you. So let me not go into detail, but just end with one final graph which probably summarizes what we have obtained. So I would like to explain what this diagram is. The horizontal axis of this diagram is a total coordinate, H11 plus H21. So, for example, in this recent work by Taylor, etc., the maximum number of elliptically fibered Calabi-Yau is somewhere here.
It's over 500 for the H11.
Oh, okay, so it's more like here, right? And this blue line indicates the upper bound for the dimension of the lowest conformal weight operation. The upper bound for the conformal weight of the lowest conformal weight of the non-linear sector. So this is delta plus delta bar is 1. So this is a vacuum. This is where the vacuum representation is. This is where the first non-terminal BPS state is. So there are lots of cases where the first non-terminal non-BPS state appears below this line. So generically, you see that when the total host number of Calabi-Yau is less than something like the 125, the mass of Higgs, then we start seeing that the non-BPS states are the dimension of the non-BPS state are lower than the first non-trivial BPS states. And then it starts going down. Look like it's actually asymptote to 3/4, but in fact it's very slow move, but it eventually goes down to just 1/4. And the interesting thing is that density grows linearly, so in this domain. So that means that there will be increasingly large number of non-BPS states going here. So what does it mean? Well, one can speculate what it means. Typically what we know in conformal Q theory with target space is that you start getting this kind of dense low-lying state, which asymptote to the continuum. That happens when the size of the target space, the radius of the target space grows. So one possible interpretation is that there is something like the minimum amount of volume complication of topology. That if you want to have more and more complicated topology, maybe you need to grow the size of the Calabi-Yau. I'm told that that's something that happens in lower dimensional manifold, like two-dimensional Riemann surface or real three-dimensional manifold, that if you want to increase more and more sort of the topological invariance, then you need to normalize the hyperbolic problem, the size has to grow in some way. And then, so maybe there is something like that for a Calabi-Yau manifold, or maybe this is an indication of some pathological features of Calabi-Yau manifold with large host number. And it's suggesting that indeed there must be finite number of topological types. That's the total speculation. So with that, I'd like to end. Thank you for your attention. This result applies to any equal to conformal symmetry with spectral flow symmetry, but with additional assumption that there is no enhancement of symmetry. That there is no sort of cross-term between vacuum representation and other representation. That's the only assumption I used. Other than that, modular invariance that applies to any conformal theory. It is true that maybe the case that not all conformal view theory of this type are related to Calabi-Yau. There are examples of mirror or rigid Calabi-Yau, for example. So this result is potentially broader than that, but I just stated it in the language of geometric Calabi-Yau. Martin?
Do you have explicit examples of Calabi-Yau threefolds with large numbers of non-parallel primaries of dimension less than 1? And so, what's the largest number that you can get?
Well, so your question was that what is the Calabi-Yau manifold? Where the Calabi-Yau manifold is? Not fast enough to be BPS, non-BPS.
Maybe with multiple non-trivial non-parallel primaries below 1.
Well, that appears. So this proves. So our theorem proves that it appears from somewhere at the total host number of 125. I don't remember exact number. I made it up.
When you know of examples of 3 or 4 or 5 or more of these below 1?
I can, because this is sort of based on the inequality. And so I can say that if you increase this, then there will be more. And I can if you ask exactly how many at 700, I should be able to tell you that there is at least, say, 5 or something like that. But also there are exactly solved cases like Lipton model or Ooguri, for which one can try to check this. However, typically those have enhanced symmetry, so that might not be precisely along the line of this general setup.
Some comment, I mean, if you take this issue, which is later unrestrained singularity, that's becoming a monkey, and you fiber this over to one, then you get this example, it's 1160.
What are you referring to?
I mean, this example is the maximum of this H1 is 400.
Yeah.
Yeah, so if you take this extreme case 3, fiber over to one,
Okay.
get the one with the highest order number.
Yeah.
Over H1. If you do it again, fiber over to one, you get the highest fourfold.
Oh, okay.
And I said you can do it with a very good school.
I see. Okay. So that's very interesting. I forgot to say that our result, because I just mentioned the result for Calabi-Yau 3-fold, that can be easily extended up to Calabi-Yau 5-fold. Beyond that, actually, there is some. So if you increase the dimension of Calabi-Yau, the dimension of the Jacobi form becomes larger, and so then it becomes more difficult to control. So in principle, it's doable, but we haven't done it. Thank you.